We'd like our Turing machines to eventually halt, either by reaching the halt state or by crashing. To do that, we might imagine a sanitizer S that determines whether or not a Turing machine will crash or halt on some input. But it's possible that the sanitizer might run forever on input X. So we need another sanitizer S prime that determines whether S will halt or crash on the input. And then we need another sanitizer S double prime to check to see if S prime will run forever on the input, and so on. To avoid this endless regression, imagine some function h, whose input is tau, the description number of a Turing machine. We'll define h tau as 1 if our Turing machine halts on every input, and 0 otherwise. So if we want to create a sanitizer, we can focus on the Turing machines where h tau is 0. So for example, let's interpret hk equals 1 and hk prime equals 0. So hk equals 1 means that vk, the Turing machine with description number k, will halt on every input. In other words, vk of x will either produce y, the function value, or crash. On the other hand, hk prime equals 0, so there's at least one input x where vk prime will run forever on input x. Next, we'll introduce the idea of a universal Turing machine, UTM. The universal Turing machine can simulate any other Turing machines. In function terms, given the description number k of a Turing machine and some string x, the universal Turing machine can evaluate vk of x. In other words, what happens when x is input into Turing machine k. Without going into too many details, a universal Turing machine can be viewed as a 3-tape Turing machine. The first tape corresponds to the input kx, where k is the description number of a Turing machine and x is an input string. The second tape corresponds to the current state of the k Turing machine, and the third tape corresponds to the current tape of that machine. Since multi-tape Turing machines can be rewritten as single-tape Turing machines, then the universal Turing machine is also a Turing machine. Now let's introduce another function, delta, where delta of k is going to be vkk plus 1 if hk equals 1, and 0 otherwise. So remember that hk equal to 1 means that the Turing machine associated with description number k will eventually halt or crash. So this vk of k is going to have a definite value, and then we'll just add 1 to it. And if k does cause our Turing machine to crash, we'll assign it some arbitrary value, like not a number. Now, if k does not correspond to a Turing machine, then delta k is going to be 0. Note that delta, because it has to evaluate vk of k, must be able to simulate any other Turing machine, so it must itself be a universal Turing machine. Now, so far we haven't assumed very much about our functions h and delta, so let's think about this. Since we introduced Turing machines to expand the capabilities of push-down automata, and we introduced push-down automata to expand the capabilities of finite automata, then the natural question to ask is, do we need to create a new type of machine to expand the capabilities of Turing machines? And if we do, will we have to create yet another type to expand those capabilities, and so on? Let's assume that h is some omniscient algorithm, so we don't have to worry about how it finds its output, only that it does. This means we can always input into delta both k, the description number of some Turing machine, and h of k, indicating whether the Turing machine will halt on every input. So delta can also be a universal Turing machine, where if we initialize and input delta 1k, that means that the Turing machine k will eventually halt. Then we could eventually arrive at a halt state, having evaluated vk of k plus 1. On the other hand, if we initialize with q0 0k, that means that the Turing machine k might not necessarily halt, and so we return h0 delta. And note that in either case, delta eventually halts. So if e is the description number of delta, then we have h of e equal to 1. And so delta of e will be phi of e plus 1. But phi sub e is the function delta, and so delta e equals delta e plus 1, which is impossible. And this means our initial assumption must be false. And that initial assumption is that there was some way of determining whether a Turing machine would halt or run forever. And consequently, there is no algorithm that can determine if an arbitrary Turing machine halts on all inputs.